Hi, welcome to your 6-6 flip video. 6-6 is talking about one thing and one thing only, and that is percent error. And this is really tying in all of our knowledge about fractions, decimals, and percents, and we need to use that knowledge to calculate how far off an estimate or guess about a value is from that actual value. So it's really one equation, and that's percent error equals the absolute value of the estimate minus the actual over the actual. So just a brief reminder that absolute value is the distance a number is from 0 on the number line. So let's draw a quick number line. So there's a quick little number line. So if I wanted to know the absolute value of 2, well, positive 2 is right here on the number line. So how far away is it from 0? Well, it's 2 units away. Similarly, if we wanted to find, so it's at positive 2, the absolute value of negative 4, well, negative 4 is right here. So how far away is that from 0 on the number line? Well, it's 4 units away. So, distance can't be negative. It's negative 4, but that's in relationship to the 0. It's 4 units, right? Here's 1 unit, here's another unit, here's another unit, here's another unit. It's 4 units away. So the absolute value of negative 4 is equal to just regular 4. All right? So the general rule is, positive 2. The absolute value of 2, that's the same thing as absolute value of positive 2. So I'll put a little positive here. If it's positive, leave it alone. If it's negative, chop off the negative. Okay? So we're basically forcing, when we take the absolute value, we're forcing a number to be positive. Okay? So we're going to take the absolute value of the distance, the difference between the estimate and the actual value, and divide it by the actual. So we're basically saying so when we do this part up here, the estimate minus actual, we're saying how far off was our guess. We're calculating how good or bad our guess was by figuring out, okay, I was only 3 away from the actual value, or I was 5 million away from the actual value. Why is the actual amount your denominator? Because we want to compare our guess to the actual amount. We don't want to compare our guess to our guess. We already know what our guess is, and we know that our guess is 100% accurate to our guess because we guessed it. So we want to compare our estimate to the actual. We want to compare estimate to actual to see accuracy. Okay, so that's why it's not overestimate, because we want to see how accurate we were. We want to compare it to our actual value, because that's the one that it actually is. Okay, so we're going to use this equation, percent error equals the absolute value of estimate minus actual over actual, to solve for some problems. So here are a couple, and I used Eve to represent estimate and A to represent actual, and we're just going to solve. So we'll work our way left to right, and they'll get harder as we go. So the first one's easy. Estimate is 5, actual is 6. So percent error equals the absolute value. Now my estimate's 5, so absolute value of 5 minus actual, my actual is 6. So absolute value of 5 minus 6 over 6. And then we work our way through. So absolute value is similar to parentheses, so that's the first thing we do according to PEMDAS. So 5 minus 6 is negative 1, so I get the absolute value of negative 1 over 6. And now we know absolute value is chopping off that negative. So how far negative 1 is away from 0 on the number line. So it just turns into 1 over 6. But you got to remember, our goal is to answer what's the percent error. So our answer should be a percent. 1/6 isn't a percent, so let's turn it into a percent. 1/6, using long division, gives me 0.16 repeating as a decimal, so I can turn that into a percent. That's 16.6 repeating percent. So you just multiply by 100, aka move your decimal 2 to the right. So the percent error, if my estimate was 5 and the actual number was 6, was 16.6%. All right, we're going to use the same process for the estimate of 523 and an actual value of 415. So percent error equals absolute value of 523 minus 415 over 415. 523 minus 415 is 108. So I have the absolute value of 108 over 415. Absolute value of 108 is just 108. So 108 over 415, that gives me 0.2602 as my decimal form. And I can change that into a percent, 26.02%. Just multiply by 100, move your decimal point 2 to the right. All right, so for this last one, estimate is 1/4, actual is 3.4. There are two different ways we can solve this, and I will show you both of them. In order to do this, I'm going to have to erase our little number line from before, so we have room, because it's going to, I know that it's going to bleed over into this space. So we have fractions and decimals, so let's set that up. All right, so percent error equals 1/4 minus 3.4 over 3.4, okay? So we can either do fractions or decimals, and we get to choose. So let's do the fraction part first. So I'm going to change everything to fractions. So percent error equals 1/4, and now I know 3 and 4/10 is the same thing as 3 and 4 over 10. So 3.4 changes into 3 and 4 over 10. I'm not going to simplify for right now. So I have absolute value of 1/4 minus 3 and 4 over 10 over 3 and 4 over 10. So I need to get a common denominator. Okay, sorry, that was that step that I just narrated. So now I turn them all into improper fractions. So 3 and 4/10 turns into 34 over 10. So both the 3 and 4/10 in both the numerator and the denominator both turn into 34 over 10. All right, so now PEMDAS, parentheses, so that in this case is our absolute value, parentheses. How do you get, we need to solve for what's inside. How do you do 1/4 minus 34 over 10? Well, you're going to need common denominators, so let's set that up. I know, looking at 4 and 10, I know my common denominator is going to be 40. So how do you go from 1/4 to something over 40? Well, how do you go from 4 to 40? You multiply by 10. So if I do it to the bottom, I do it to the top. So 4 times 10 is 40. 1 times 10 is 10. Now I'm going to do the same thing for the 34 over 40. 10 goes to 40. You got to multiply by 4. So 10 times 4 is 40. 34 times 4 is 136. So I got common denominators there. That's all I did. Everything else stays the same. Okay? And I needed common denominators because when you add or subtract fractions, you need to have the same denominator. Okay? So I have 10 over 40 minus 136 over 40. Absolute value of that over 34 over 10. So I can simplify. 10 over 40 minus 136 over 40 gives me negative 126 over 40 because you just subtract the numerators. 10 minus 136 is negative 126. Everything else stays the same. And now I get absolute value of negative 126 over 40 over 34 over 10. Now I can take the absolute value, get 126 over 40 over 34 over 10. So this is a complex fraction. We talked about this in our last unit. And we can solve that because I know that that is the same thing as 126 over 40 divided by 34 over 10, right? Because a fraction just means division. So 126 over 40 over 34 over 10 is the same thing as 126 over 40 divided by 34 over 10. And now it's just the division of fractions. So this turns into 126 over 40 times, keep, change, flip, 10 over 34. And now I can just multiply numerator by numerator, denominator by denominator. So 126 times 10, 40 times 34. I get 1260 over 1360. Wonderful. I got a fraction. Let's make it a decimal. 0.9264. Am I done? No, I need a percent. So I got to change that decimal to a percent. 92.64%. All done. Okay. So let me back up for a second. Our second option is to do everything through decimals, because this was a lot of work to solve through fractions. Fractions are typically more work because you got to get common denominators for adding and subtracting. You got to make sure that, you know, complex fractions work out. Decimals are a little bit simpler. So let's see how it goes with decimals. I'm going to start off with the same thing. Percent error equals 1/4 minus 3.4, absolute value of that over 3.4. So let's just change all my fractions to decimals. So 1/4 is 0.25. So this just changes into absolute value of 0.25 minus 3.4 over 3.4. That's pretty easy. 0.25 minus 3.4 is negative 3.15. So it just changes into absolute value of negative 3.15 over 3.4. That's pretty easy to solve. Absolute value of negative 3.15 is 3.15 over 3.4. That's just a fraction. I can divide that and turn it into a decimal using long division. So if you go into your calculator and divide that, you get 0.9264, which turns into 92.64%, which is exactly what we got. This is exactly what we got the other time. Okay? So it doesn't matter if you do decimals or fractions, you get to the same point. All right? Next thing is, what do you do if you're given percent error? How do you solve for the missing pieces? So if you run a computer simulation which calculated your percent error to be 1.2%, you see from your notes that your actual value is 50. What was your estimate? Okay, so I'm going to rewrite our equation. Percent error equals estimate minus actual over actual, and I'm going to take the absolute value of that numerator. So let's highlight important information. 1.2% is my percent error. Your actual value is 50. I want to know what is your estimate. So let's plug in what we know. My percent error is 1.2%. Let's use x to represent my estimate. And both of my actual values were 50. All right, so now let's solve for x. How do you solve for x? Well, I have x in the numerator. I'm dividing the absolute value of x in a number by 50. So let's try and simplify this as much as we can. How do you get rid of that 50 that's being divided? Well, you multiply, oh, well, hold on. Whoop, too far. Let's change 1.2% to a decimal, divide it by 100, aka move your decimal point 2 to the left. 1.2% is 0.012. All right, now everything else stays the same. Now, how do you get x by itself? You have that absolute value being divided by a number. Let's get rid of that divide by 50. How do you get rid of divide by 50? You're going to multiply both sides by 50. Those guys cancel out. And you get 50 times 0.012, which is 0.6, is equal to, now when those 50s cancel out on the right-hand side, you're just left with x, the absolute value of x minus 50. The point of an absolute value is to ensure that your answer is positive. 0.6 is positive, so I can just get rid of those absolute values. If 0.6 was negative, I would have to get rid of that negative value if I wanted to get rid of these absolute values, okay? So if it's positive, you can just get rid of the absolute value. If this 0.6 is negative, then you need to get rid of that negative in order to get rid of those absolute values. Okay, but it's positive, so let's leave it alone. So I get 0.6 is equal to x minus 50. This is an easy one to solve. How do you get rid of the minus 50 next to your x? Well, you're going to add 50 to both sides. So you get x is equal to 0.6 plus 50. So x is equal to 50.6. So your estimate was 50.6. The actual was 50, so you are 1.2% off. All right? The last thing I want to talk about is how far away a number is from, like if you compare 2% errors, how do you know which one's bigger or smaller? So this is kind of like a little scatter plot diagram that you've seen. We talked about this in class. If you have weight, or you could also have like length or some measurable quantity as your x-axis, and then frequency as your y-axis. Each little dot would represent one thing. So how many total things were measured in whatever this experiment was? Well, I had 3 here, 2 here, so I'm at 5. 4 here, 9, another 2, 11, 12, another 4. I tested 16 total, let's say this was measuring the weights of rocks. So 16 total rocks, or whatever. I'm going to get rid of the word rocks. I'd rather put data points, okay? So if you're comparing percent error, and your actual was 0.4. So you had all this and you decided, and you looked up in a textbook that the actual weight of this special type of rock should be 0.4 milligrams or whatever it is. Which one of these have the greatest percent error? So what you do is you're looking how far away are all of these from the actual. So we know that 0.3 is 0.1 away from 0.4. And on the same side, 0.5 is also 0.1 away from 0.4. So the percent error for 0.3 and 0.5 are equal to each other because they have the same range. All right, 0.2 is 0.2 units away from 0.4. And on the same side, we can say 0.6 is 0.2 units away from 0.4. So these guys would have the same percent error. All right, so which one has the largest percent error? Well, 0.7, because it has the largest distance between them. So this has a distance of 0.3. So let's calculate that percent error. So we know, I'm not going to rewrite the equation, but percent error is equal to the absolute value of estimate. So if our estimate was 0.7, because that was the one we're looking at here, 0.7, so 0.7 minus my actual, which is 0.4, absolute value of that over my actual 0.4. So we can solve now and determine the the percent error. 0.7 minus 0.4 is 0.3. So I'm going to take the absolute value of 0.3 over 0.4. So this is 0.3 over 0.4, because the absolute value of 0.3 is just 0.3. And then you can solve this. You could either multiply by 10, excuse me, to get 3 over 4, which is an easy calculation. You could also go into your calculator and do 0.3 divided by 0.4. Either way, you'll get 0.75, and then we convert that decimal to a percent, 75%. So your percent error, if your estimate was 0.7 and your actual was 0.4, would be a 75% error, okay? But the point I really want to drive home here is that your percent error is the same regardless of what direction you go. 0.2 to 0.4 has the same, if 0.2 is your estimate and 0.4 is your actual, 0.2 has the same percent error as 0.6 because they're the same distance away. You know, we can do the same thing for 0.5 and 0.3. They're both 0.1 away, so they'll have the same percent error, okay? And that was it. Let me know if you have any questions.